All right, very good. Thank you very much. It's a great pleasure to be in this nice place where I have never been before. Let me apologize to some of you have heard a very similar version of this talk last month or a month and a half ago at a previous time when I was in Europe. So those of you who have heard me speak recently can just go to sleep or go get more coffee or something. You don't have to worry about this. So what I want to talk about is thinking about these non-equilibrium experiments in correlated materials in terms of energy landscapes. And the work I want to tell you about is done with two really outstanding groups of theory collaborators, Alex Georgescu, who was a postdoc with us at the Flatiron Institute and is now just beginning a faculty position in the Department of Chemistry in Indiana, and Jiwon Sun, who was a postdoc at Columbia after doing a PhD with Misha Fogler in San Diego and is now in Beijing, and Denis Golesh, who was in Ljubljana. And the work was inspired by two experiments, an old one that I'll describe briefly from Rick Avrett's group, and new experiments that have just been appeared on the archive in the group of Andre Singer at Cornell. I also have to say that the work was supported by the United States Department of Energy through the ProQM Energy Frontier Research Center and by the National Science Foundation through the Columbia Materials Research Science and Engineering Center, as well as the Simons Foundation. All right. Okay. So as I said, what I want to talk about is energy landscapes for non-equilibrium dynamics of correlated materials. I will start by briefly outlining the experiments that inspired this work, then talk a bit about equilibrium free energies and how you take these concepts into the non-equilibrium domain. Okay, so first set of experiments were done by the Rick Averett group on this that I want to talk about, were done by the Rick Averett group on this particular high TC cuprate material. This is work that was inspired by work done previously in the group of Andrea Cavalieri. So this material is a member of the high TC cuprate family, and it has a slightly involved phase diagram in which at particular carrier concentrations, the superconductivity is suppressed by the presence of a competing order, two kinds of competing order whose names are CO and SO, which stands for charge order and spin order. But for this purpose, all you need to know is that they're bad. Whereas if you change the carrier concentration a little bit, then these other bad things more or less go away and superconductivity comes back. Okay, so what they did was do a ultra-fast experiment where they pumped the material above the band gap at the usual 1.5 eV, thereby raising the electronic temperature well above the superconducting transition temperature, and then seeing what happens. Okay. And so what happens is as follows. All right. Here is the measurements. They interrogate the system after pumping by looking at the transport in one particular direction, the so-called c-axis direction. And what they want you to see is that in equilibrium, you have a very weak, almost non-detectable superconducting state. That's the gray thing. And after pumping, you get a very long-lived superconducting state. And a signature of the very long-lived superconducting state is that the imaginary part of the conductivity, which is telling you about the reactive response, becomes very large, meaning that there's something which can just slide back and forth without any resistance. So that's the result. You blast it, thereby raising the electronic temperature, and superconductivity magically appears to get stronger. Okay, so that's one set of experiments. The other set of, and this was published in Proceedings of National Academy in about 3 years ago. The second thing I want to talk about is a material that has a correlation-driven metal-insulator transition, calcium-2 ruthenium-O4. So what you need to know about this material is that as you lower the temperature, it has a first-order transition at a temperature a bit above room temperature. You see it here in the plot of resistance versus temperature, where the resistance starts out more or less metallic. It's flat and not that high, and then it jumps and becomes obviously insulating. And the metal-insulator transition is associated with a change in the crystal structure. In this case, it's an isosymmetric change, meaning that the crystalline symmetry of the material above and below the transition is the same, but the atomic positions change. In particular, the important structural unit is this ruthenium-oxygen octahedron, and basically the thing gets flatter when you go below the transition temperature. The apical bond length gets dramatically shorter, the in-plane one gets longer. That's shown here. So there's a coupled electronic and structural transition. Okay, so that's equilibrium. Now, what Andre and his student or postdoc, I forget which, Anita, did was, and it's explained in this paper, which is primarily an experimental paper, is again, they excited it, they pumped it with an above bandgap laser at the same 1.5 eV, and they simultaneously measured three things: the transmission at a high energy around the bandgap energy, the transmission at a low energy in the lower terahertz range, and they measured the lattice structure, in particular the c-axis lattice parameter, which is associated with this flattening of the octahedron. And the c-axis lattice parameter is presented as the actually 008 scattering Bragg peak. So a lattice parameter getting longer means that the position in momentum space gets lower. Okay, and what you're supposed to see here is first, you blast it at time 0, and then immediately you see a change in the high frequency reflectivity, indicating that you've done something dramatic to the carriers that respond around the edge of the bandgap. On a slightly longer time scale, which you can see here, that's the black thing, the structure changes in this way so that the c-axis lattice parameter gets longer. And on a yet longer time scale, the low frequency reflectivity, that's this purple thing, changes, indicating that you're recovering a metallic state. Okay? And then all of these things last a very long time, meaning ballpark of 100 picoseconds. Okay, so what you get is a long-lived change of state with different rise times. Okay, so that's the experiments. Oh, and the other thing I meant to say, the other characteristic of this experiment, and also although Kremen and Averick didn't put it really in their paper, these experiments have a noticeable fluence dependence. If you hit the material relatively lightly, that is to say at a low fluence, you see here, basically you get little changes but no shift in the peak. You hit it a little harder and you see, although it's a little hard to discern here, a sort of wobbling of the peak. The maximum is here, it gets a little smaller, then it goes back. You hit it harder, it just goes to a new state and stays there, right? So there's a fluence dependence to all these effects. A weak pump doesn't do anything. A strong pump puts it into this long-lived state. Okay, so that's the experimental situation. Oh, I'm sorry, I keep getting out of order here. The other thing I wanted to say, and this is an experimental result, is that while, of course, the big worry about all of these experiments is that, particularly with temperature-driven metal insulator transitions, is that what the experiment is doing is just heating the sample. All right? So the argument against is slightly involved, but I wanted to walk you through it. Basically, you can look at the intensity of the same Bragg peak that I showed you. In the insulating state, generically that intensity is small in a sort of ideal crystal state, basically because of destructive interference. They're looking at some particular high-order Bragg peak, and there's a large amount of destructive interference, so the intensity is weak. And what that means is that, unlike in other cases, once you start adding disorder, the intensity goes up because you get random atomic positions which mess up the scattering condition, which cause the scattering waves to destructively interfere. Okay, now, this is a plot of the intensity of the peak in some units versus the change in position of the peak. This is the thermal effect. You go through the metal insulator transition in equilibrium, and the peak position changes, and the intensity changes, because you're getting both a higher temperature and you're going into a new state. Whereas in the non-equilibrium experiment, while there is some increase in the intensity, the change in peak position is way big compared to the intensity. So that's an indication that the state you have is a genuinely non-equilibrium state, that you have a large shift in peak position, like you have at high temperature, but much less disorder. All right? So, and indeed, all of this stuff is to the left of the big upturn, which is associated with the metal-insulator transition. So that's the evidence that what one is seeing is not just heating. OK, so with that as preliminary, let me now talk about theory. OK, so look, as we all know, integrating the time-dependent Schrodinger equation to find a time-dependent many-particle wave function and state is hard. So you need a simplified description. And the description I would like to propose to you is based on familiar Landau theory. Right? So you all know if you're talking about equilibrium, you have some kind of order parameter, which I've written here as psi, and you can write a free energy as some kind of expansion in powers of this psi. And the important thing is that there's a coefficient of the second order term which changes sign, thus indicating a transition. And just as a little note, for historical reasons which I can't justify, we used an unconventional sign. There's a minus here, so this coefficient being positive means that you're in the ordered phase. OK, so what I really want to do is take Landau theories like this, all right, and interrogate their time dependence by assuming you have what in the language of dynamical critical phenomena is called model A dynamics, which just means you have some kind of relaxation. You move the free energy off of the minimum, that gives a force, and the thing evolves linearly with the force, and there's some kind of noise. And the magnitude of the noise is controlled by the fluctuation dissipation theorem. It has to do with the temperature. OK, so this is a theory, all right? And now the first question I want to ask is, going back to the Rick Everett experiment, suppose that I have some kind of ultra-fast experiment where I hit the system, and that creates transient heating, all right? So then we can consider model A dynamics, which is this, but with a time-dependent temperature. Right? So the picture is, again, the pulse instantaneously heats the sample, then you turn the pulse off, the temperature relaxes back to equilibrium, and the order parameter follows this, or order parameters follow this around in some way. OK, so here we considered a model with two competing order parameters that have two different time constants. All right? So this picture, which is a little bit hard to read, is supposed to show you sort of the equilibrium free energy landscape. So we have two fields. There's a term in the free energy which makes them compete with each other if this or cooperate. If this coefficient is positive, then if you have two, you don't want to have one, and conversely. So that gives you this free energy landscape where there is two minima, one associated with field 2 and one associated with field 1. Right? Then if there's a time-dependent theory, which I've written here, and then the interpretation is in your ultra-fast experiment, if you heat the system above the transition temperature for both fields, that will take this energy landscape, which has two minima, and kind of fold it up so it only has one sharp minimum around 0. Then as the system cools down again, the free energy landscape unfolds into this, and the system moves in that energy landscape. And the interesting point is if the dynamics of field 1, let's say, is faster than the dynamics of field 2, it can roll down its hill into the wrong minimum before field 2 has time to grow. OK, now I'm not going to go into any of the theoretical details, but I did want to say for any theorists in the audience that basically if you have a small Ginzburg parameter for the equilibrium transition, meaning that this mean field-like description is more or less good, then you also have a controlled theory of dynamics controlled by the same parameter. And the second thing for those of you who like this is that you can view this as a kind of variant on the Kibble-Zurich criticality, if you know what that is. And if not, don't worry about it. OK, so here's the picture. The pulse quickly drives the system to a high T state. So our second order coefficients, alpha here, start out positive. That's the ordered state. They get slammed to negative values. Here we've said that in equilibrium, field 2 is favored, so this is larger. That means that when you raise the temperature, it's still larger, although they're both negative. Then you turn the pump off, the two fields relax back to their equilibrium state, and the order parameter does something. In fact, it does two things. One, as you slam the thing into the high temperature state, the order parameters collapse to 0. That's what you see here. Then you turn this off, and they start to grow again. All right? It's a little subtle because the equilibrium favored state, of course, starts out closer to 0. So when the temperature rises, it crosses 0 sooner so that the order parameter favored in equilibrium starts to grow sooner. But if its dynamics is slower, the unfavored order parameter, which starts later, grows more rapidly. And as it grows, it creates its own amplitude, which acts to suppress the more favored order parameter. All right? So the result is that you wind up rolling down the hill in this direction and being stuck in minimum 1. Now, there's a bunch of other things to say about this, which I haven't time for, relating to the structure of the fluctuations that you get in the two order parameters. But you can see what happens. Now, there's another related thing you can do. Suppose that the order parameters cooperate, so the coupling energy is just slightly negative. All right? So that means that the favored state in equilibrium is one which is not just order parameter 2, but has a little bit of order parameter 1. That's the situation in this cuprate material, where you have strong spin and charge stripe order and weak superconductivity. All right? Then you can play exactly the same game. If you make a weak pump, then our solution of the time-dependent equation shows that the order parameters relax towards 0, but not all the way. Then you turn the pump off, and it goes back to the minimum that it was in. Whereas if you make a strong pump, it rolls over to here and then goes down to the purely superconducting minimum without any charge order. All right, so this is on one level pure phenomenology. And given that we have a Landau theory with a couple of parameters, we can choose these parameters to reproduce the experiment. All right, but I think it shows what's going on in this kind of experiment. That basically, if you hit the thing hard enough, you're unfolding the free energy, and then the thing which has faster dynamics, namely the superconductivity, which is purely electronic, all right, evolves faster than the charge order, which involves a lattice degree of freedom, so it has a rather slower time constant, right? And then the system winds up in this metastable minimum. And an important open question that we have nothing useful to say about at this point, but which I think is an important next step in the field, is how do you understand the timescales for the system getting out of this minimum and eventually relaxing back to here, right? And of course, we know in general about tunneling and escape from metastable minima and supercooling. But how that theory, which is understood in equilibrium, applies to these kind of correlated coupled order parameter systems, I think, is not yet known. OK, so that's topic 1. Topic 2 is metal-insulator transitions, which are a slightly involved variant on this, because now you really have explicitly electronic and lattice degrees of freedom that are coupled. And let me give you 2 examples of materials where this coupling is important. First, the rare earth perovskite nickel oxides. Right? These guys have a metal-insulator transition whose temperature depends on which rare earth you put here. Lanthanum does not have a transition. Praseodymium, neodymium, samarium, europium, lutetium have metal-insulator transition temperatures, which vary with material. The metal-insulator transition is associated with a strong disproportionation where the octahedron around one nickel gets small, and the charge on that nickel gets less, and the octahedron on the next nickel over gets big, and the charge gets more. So there's a coupled electronic and lattice rearrangement at the transition. Right? So this has been known essentially forever. All right? Another thing I wanted to point out is that, in fact, if you change the substrate to impose strain conditions, you can strongly affect the transition. In particular, if you grow it on this substrate, the transition doesn't exist, whereas if you grow it on this substrate, you see a transition just slightly suppressed from bulk. OK. Here's our friend the ruthenates. Same deal, I already told you that. In this case, unlike the nickelate case, the transition is isostructural, meaning that the lattice deformation has the same symmetry in both cases rather than breaking some additional symmetry. But otherwise, same deal. You have a change in electronic structure from the 3 nickel d orbitals being approximately equally occupied in the metallic phase to 2 electrons in x, y, 1 in each of these 2 in the insulating phase, and associated with that a strong structural deformation. All right. And again, there is a strong dependence of this transition on the substrate. OK. So You got an electronic order parameter. It's linearly coupled to lattice degrees of freedom. It's controllable by pressure, strain, et cetera, and first order transition. OK, so let me just skip over this because I'm going to run out of time and say that we're dealing with first order transitions here, right? And so how you think about first order transitions, it was explained by Alex Georgescu in this paper. OK, we know from various theories of correlated electrons that if you just do calculations at a fixed structure, you get results that are consistent with experiment. If I take the actual structure in the metallic phase, I feed the thing into my correlated electron machinery, I get a metal. I take the structure in the insulating phase, I feed it into my material, and I get an insulator. All right? But knowing why the system should adopt that structure is a different question. All right? So what we can do in our correlated calculations is essentially determine the electronic configuration at fixed positions of the atoms. In other words, we get an equation of state which says electronic structure as a function of physical structure. Again, because I don't have time, I'll refer you to this paper to say how we can infer from our equation of state what the full free energy is, and I'll just show you the free energy. All right? So for this guy, what you get is a free energy which makes you think you're doing string theory. You have this kind of trousers diagram where this is the minimum in the undistorted state, and then you have a minimum where you have a substantial lattice distortion and a substantial electronic structure distortion. And you will notice that there's no other minima, that you need both the lattice degree of freedom and the electronic degree of freedom to get an insulating state. So in this material, the electronic and lattice contributions to the metal-insulator transition are strongly intertwined. There is no purely correlation-driven metal-insulator transition. There's also no purely lattice-driven metal-insulator transition. You need both physics coupled to get the transition. OK. You can understand things which I'll have to leave aside here about consequences for films. But the one thing I did want to point out, this is going back, I think, to Ankit's data, is that, in fact, if you grow things on the substrate, your natural thought as a theorist is that you're changing the quadratic term in the Ginzburg-Landau theory. That is, in effect, the transition temperature. And that's not what's happening. The thing that the substrate is doing is changing the nonlinear terms that give you the larger structure in the free energy. OK. More or less same story with calcium ruthenate. In purely electronic terms, the undistorted state is minimum. You get a strongly first-order transition, which gives you this free energy landscape. All right, so now in conclusion, let me again just skip over this and talk again about the non-equilibrium experiments. All right, what we did, and by we, in this case, I mean Dennis Goles, who has developed very sophisticated methods for solving these correlated dynamical mean field theory equations as a function of time, but this is still within the general framework of integrating the many-body Schrodinger equation forward in time and seeing what happens. He can calculate what happens after an optical excitation. So an optical excitation excites some particles over the band gap. That gives you a population imbalance. And then he can study over a 10 to 100 femtosecond time scale what happens to that population imbalance. All right? So we do that, including the lattice degrees of freedom in this sort of semi-classical way. And you see this interesting thing, that if you have a low fluence, that's the red curve, what you get is oscillations around a state which is basically equivalent to the insulating one. You make a larger fluence, parameterized theoretically here by just how much initial population imbalance you get, and what you see is a evolution over the time scales accessible to him towards the insulating state. Now, you will notice that these time scales are femtoseconds. To get these scales, to get even to this scale, we had to make a further approximation, which is that we reduced the phonon mass so that the lattice time scale was short enough that we could live with it. That's why you see these oscillations are basically the phonon frequency in our calculation, and they're on the 5 to 10 femtosecond time scale. All right. But still, what you see is a fluence-driven dynamical detrapping. And the interesting thing to do is to plot the electronic disproportionation and the lattice distortion on our equilibrium free energy diagram. And again, what we would like to argue is that for two things. First, for a strong enough fluence, you get kicked out of the insulating minimum and you go over the saddle point and can decay into the metallic minimum. And second, in all these calculations, there's a severe electronic bottleneck. Basically, the electron distribution has a very hard time relaxing across the insulating gap. All right? So the way it works is that you first make an electronic disproportionation. That puts you somewhere over here. Then that makes a force on the lattice, which drives the lattice distortion down. And once you've driven the lattice distortion down far enough, then the system can slowly relax into here. So that the electronic relaxation has to wait for the lattice in these compounds rather than the other way around. All right, so I'm out of time, so I'll just pop this up and thank you for your attention and apologize for running over.